To solve AX congruent to D mod B, we noted that solutions to this congruence were integer solutions xy to AX minus BY equals D, which correspond to solutions to the congruences AX congruent to D mod B and minus BY congruent to D mod A. While the first congruence is the same as the original, the second is generally simpler. Then lather, rinse, repeat until we have a solution. Now our approach works even if the modulus is composite with a couple of qualifiers. If the greatest common divisor of A and B is 1, then AX congruent to D mod B will have a unique solution. But if the greatest common divisor isn't 1, then our congruence might have no solutions or multiple solutions. For example, let's try to solve, if possible, 6x congruent to 5 mod 15. As before, solving 6x congruent to 5 mod 18 requires finding integer solutions to. And we could stop at this point because the greatest common divisor of our coefficients 6 and 15 is not a divisor of 5, so this equation has no solutions. But remember, sometimes it's useful to make bad decisions. Let's see what would happen if we continued. So to find integer solutions to 6x minus 15y equal to 5, we'd solve the congruences. And again, that first congruence is what we started with, and our second congruence can be simplified. So we need to find integer solutions to 3y minus 6z equals 5. So again, to find integer solutions to this equation, we'd solve the congruences, where, again, our first congruence is what we started with, and our second one is impossible. So here at this point, we see that we can't actually solve the congruence, which means we can't solve the equation. Now you might wonder why we did that. Well, it was easy to determine that the greatest common divisor of 6 and 15 didn't divide 5. This won't always be the case. And while we could quickly determine the greatest common divisor of two numbers using the Euclidean algorithm, note that if we applied the Euclidean algorithm in this case, we'd get. And notice that the remainders were the coefficients in our second congruences. Which means that it would take the same amount of effort to use the Euclidean algorithm to find the greatest common divisor, and in this case decide the problem was unsolvable, as it would be to just use our solution method. So let's consider the congruent 6x congruent to 3 mod 15. So again, solving this congruence requires finding integer solutions to. Integer solutions to this equation correspond to solutions to the congruences. And again, the first congruence is the same, the second congruence is simpler. Solving that second congruence corresponds to finding integer solutions to. Integer solutions to this equation correspond to solutions to the congruences. And again, our second congruence simplifies all the way down to an identity. Since this last congruence is an identity, then it will hold for any value of z. Now, since we're working mod 3, then z can be 0, 1, or 2, and each of these will give us a solution. So if z equals 0, we have, and x will be, if z is 1, then we have, and if z is 2, then we have, and so we have 3 solutions.